So now we will have our first remote speaker. So this is a hybrid school, not just for the attendance, but also for the speakers. And there will be Matteo Gatti from École Polytechnique in France, who is going to give you some more details about many body perturbation theory, from equations, from spectroscopy. And so, please, Matteo.
Thank you, Davide. And good morning, everybody at ICTP. It's nice to see so many friends' faces over there. And good morning or good afternoon to everybody that are following online. I'm very sorry that Lucia Running, who was supposed to give this talk, had to cancel her participation at the very last moment. I'm very sorry for her, and I'm also sorry for you because you have me instead of her. The deal is that I will use her presentation, so I will try to tell you what she had prepared for you. And so if you have any questions or any complaints, you can use my email here. So what I'm going to tell you is my responsibility. And if you have anything you want to ask or complain, you can use my email here. So the idea of Lucia's lecture was to make the bridge between what Pedro has just told you about May body perturbation theory and the equations of Green's functions theory and the applications, and in particular about spectroscopy that you will start to see starting from next lecture. So the content of Pedro's lecture was the discussion of the May body problem in quantum mechanics and the introduction of Green's functions with their properties, and in particular the Dyson equation. And the last point of his lecture is what comes next after you have introduced all these formulas. What comes next? And the answer concerning the point of view of this lecture is theoretical spectroscopy, in the sense that one of the most widely used of Green's functions theory is the calculation, is the prediction, and the analysis and the understanding of spectra. And excitation spectra are useful for many different applications. They can be new materials for solar energies, so new solar cells, new materials for memory devices, new materials for new colors for candies. So the applications of spectroscopies can be very, very different, and Green's functions are made for calculation of electronic excitation spectra that are at the basis of spectroscopy. The first question we should ask whenever we start to use a theoretical formalism is why we do what we do. So this is the first question that I will try to address in the following. Why should we use Green's functions instead of, for instance, the May body wave function or the density? So what we are interested in when we want to do spectroscopy, or in general when we solve quantum mechanics problem, are observables. And we have learned from basic quantum mechanics that if you are at temperature 0 and for a given number of particle n, is that observables are expectation values of some particular operators that are related to the specific observables, and expectation values are calculated as integrals with respect to the May body wave function of the given operator. If the system has n electrons, the final answer is maybe just a number, and at the end what we have to do is a very large integral with respect to many of the degrees of freedom in our system. So this is a very complicated object, but in principle, if you know the May body wave function, what is here is just a recipe that is telling you that if you give me the May body wave function, I can tell you which is the observable that you are interested in. You have just to perform this very complicated integral. But this is a functional that is in principle known. The only problem is that this is very complicated and you have to make a very large effort to calculate and to store this mini-body wave function, which in most cases of interest is impossible to do. And after all, after you have made this very huge effort, you are just interested in a number. So this is not a practical way to go. The alternative is density functional theory. And in density functional theory, we have learned that instead of calculating observables using functionals of the mini-body wave function, we replace these functionals with other functionals. These functionals could be in principle functionals of the external potential that defines our system. And in density functional theory, the idea is to calculate observables as functionals that in principle are different from the original functionals. And these functionals are functionals of the ground state density. And Oenberg and Kohn has told us that in principle, we can calculate all the observables, not only the observables that can be explicitly calculated as observables in terms of the explicit observables in terms of these integrals of the density, so single particle operators, but we can calculate in principle any observable meant as expectation value in the ground state wave function for in principle all the quantities that we are interested in. And this is in terms of a functional of the density, as I've just said. So instead of using the mini-body wave function as our descriptor of the system, which is what very often we do in quantum chemistry when we do simulation for small molecules where the number of degrees of freedom is limited. And this is called configuration interaction theory, or in the case of quantum Monte Carlo calculations where we make a stochastic estimation of this wave function. Instead of using this as descriptor, in density functional, we use the density, which is a more compact object, as our descriptor. And density functional theory is telling us that we can calculate everything in principle as a function of the density. But the first question that we have to answer is, where do we get the input that we have to insert in this functional, which is the density? And the answer given by Kohn and Sham is the genius idea to build an auxiliary system, which is the Kohn-Sham system, that is just meant to give us the density that is, again, the input that we need to put in our functional to obtain the observable. It's an auxiliary system because, as we have already discussed previously, the Kohn-Sham system is just meant to give us the density, but for instance, the eigenvalues of these Kohn-Sham equations are not supposed to give us information about excitation energies. The only information that the Kohn-Sham system is supposed to give us is the density. And we know that we have to solve this system of equations that are the Kohn-Sham equations, where we have the Hamiltonian, that is an effective Hamiltonian, where in addition to the external potential that describes our system, we have the RT potential that is related to electrostatic interactions, so classical electrostatic description of the system, plus a correction that is the exchange correlation potential of Kohn-Sham, that is a local potential, that is a function of the density, that is formally defined as a functional derivative of the exchange correlation energy with respect to the density. And this is the quantity that we have to approximate. So this is what Kohn-Sham gives us, it's the density, but the second problem of DFT is that for most of the cases, we don't know the functionals. So even if we have the density, we are not able to express our quantity of interest as a function of the density. And the typical example is something that has to do with spectroscopy and excitation spectra. So this is what we are going to discuss in a moment. To summarize, the exact Kohn-Sham system is designed to give us the good density. It's often used to calculate observables directly, in the sense that we use the functionals that were in principle supposed to be used in terms of the many-body wave function, but we replace the many-body wave function with the Kohn-Sham many-body wave function, and this is an approximation, clearly. And the problem is that for most of the cases, we don't know the explicit function of the density. Okay, so the quantities of interest for us in principle are functional of the density, but we don't know them. And if we use instead the original functional in terms of the many-body wave function, but with the Kohn-Sham wave function, then this is an approximation and it's not supposed to give us the good answer. Okay, this is because the Kohn-Sham system is an auxiliary system that is meant just to give us the density. And the first example where we'll discuss this is photomission spectroscopy. In photomission spectroscopy, there is some light that is used to kick out one electron from the system. So typically you measure the kinetic energy of the photoemitted electron, and you can also measure, if you do angular resolved photoemission, the angle of the emitted photoelectron. And if you combine this information related to the kinetic energy of the photoelectron and its direction, so its angle, that you can associate to the K point inside the material, what you can obtain is a collection of dots that you see on the right panel. And for instance, you can fix a given dot that corresponds to a pair of energy, binding energy, and K point that is associated to the kinetic energy and the angle of the photoemitted electron. And then you can scan the angles and the energies. And what you obtain are these dots here that correspond to the band structure of the material. Okay, this is what photomission spectroscopy is. And if you combine direct photomission that measure the occupied states with inverse photomission that measure the the unoccupied states, you can retrieve the band structure of a material. So this is the experimental definition of a band structure. Now, in the independent particle picture, what you would obtain in the description of this experiment is just the fact that you think that you are removing one electron from the material, and this electron was occupying the single particle levels at different K points if you are in a solid. And so the description is just a collection of very sharp peaks. Mathematically, these are delta functions at the energies that were occupied by the electron before being emitted from the material. So this, again, is for direct photomission, where you remove one electron from the system, you go from n to n-1. And this would be for the unoccupied levels for inverse photomission, where you add one electron to the system. Okay, so this is the independent particle picture, just a collection of delta peaks at the energies of the single particle levels. And this is also what Kohn-Sham DFT gives us. And in particular, this is a comparison between the LDA Kohn-Sham band structure on the left and the experimental results in the center right panel. And you see that this is the band structure of bulk germanium. And in particular, you see here that in LDA, you obtain a band structure that has a problem, in particular around the band gap, because LDA is giving a metallic band structure. And this is the famous or the infamous Kohn-Sham band gap problem. It's the fact that typically in Kohn-Sham LDA, you get an underestimation of the band gap. And this has two reasons. First is that we are using LDA, that is an approximation of the exact Kohn-Sham system. And second, and most importantly, it's the fact that the Kohn-Sham system is an auxiliary system that, again, is meant to give us just the density. but it's not meant to give us the band structure and also the band gap. And this is also the case in if you have the exact exchange correlation potential. For instance, you can also think that you want to calculate the band structure of the homogeneous electron gas. So in this case, the LDA would be exact. Of course, the homogeneous electron gas is a metal, so there is no band gap, but you can still compare the band structure with more advanced theories like Green's function theory, and you would see that even the exact Kohn-Sham band structure, because LDA is exact, so it's known, is not equal to the exact band structure. So even if you have the exact Kohn-Sham exchange correlation potential, you don't get the exact band structure of a material. In the case of the gas, this can be proved directly because you have the exact approximation, exchange correlation potential, and you can have very good approximation for the exchange correlation potential in materials, and you would obtain also in that case that the band structure is not equal. And the reason is that, again, I want to stress the fact that we don't get the exact band structure because we don't know how to express the band structure in terms of the functional of the ground state density. So what we have to do is we have to change the descriptor. Again, instead of using the many-body wave function and the density, we have to use a different descriptor. And in our case, the proper descriptor would be the Green's functions. And Green's functions have been already introduced by Pedro. These are describing the propagation of additional particles in the system. And in particular, I will first of all discuss about the one-body Green's function and its link to spectroscopy. So this has been already introduced, and the one-body Green's function is a function of 2 points in space and time and one frequency. And it's a function that can be expressed in this way with this fraction representation that is called the Lehmann representation. And in particular, for what is interesting for us is the fact that this function, as a function of frequency, has poles that correspond to the zeros of the denominator. And these poles correspond to the addition and removal energies that we measure in photomission spectroscopy. And these are those that describe the band structure of the material. So we use and we define the Green's function indeed because the poles of this function will be the exact quantities that we are interested in, contrary to Kohn-Sham. And in particular, a quantity that is of interest for us is the imaginary part of the Green's function. And this imaginary part of the Green's function is expressed in the reciprocal space. So you have just to take the Fourier transform of this quantity, and you go to the reciprocal space, so in K space. And then you can see that you can express this imaginary part of the Green's function using this expression here, where you have peaks at the additional removal energies that were the poles of the Green's function that are weighted by these amplitudes that are at the numerator of the Green's function that are called the Lehmann amplitude. And this quantity is of interest for us because it's called the spectral function, and it's the quantity that we can compare directly with photomission. And in this way, you see that we obtain quantities that we can compare with photomission as simple functionals of the Green's function. In particular, in this case, these are very simple linear functional of the Green's function. You have just to take the imaginary part of the Green's function, the absolute value, and you obtain the spectrum. Now, you have seen that the Kohn-Sham system is an auxiliary system where you have an effective potential that is meant to give us the density. In the framework of Green's function and the one-body Green's function in particular, we have to generalize this idea of auxiliary system. And instead of having this local and real potential, that is the exchange correlation potential, we introduce a more complicated potential, effective potential, that is called the self-energy, that takes into account all the exchange correlation effects beyond the R3 description of the system, as in the case of the exchange correlation potential of Conchamp. But it adds more features, because this new effective potential is now non-local in space. So it acts as an integral operator with respect to the wave functions. And moreover, it's frequency dependent, because the Green's function is describing a propagation in time. So it is non-local in time. And if you take the Fourier transform, it gives us a frequency dependence. So the self-energy is not only an operator that is non-local in space, but is also non-local in time. And it means that all the quantities become frequency dependent, including the wave functions, the effective wave functions that are called the quasi-particle wave functions, and the energies. So this is just a new auxiliary system that is meant to reproduce the single part, the one body in Green's function, so a more complicated object. And this means that this more complicated object requires a more complicated effective potential, that is the self-energy. You have seen that the Green's function can be calculated as a solution of the Dyson equation. And this Dyson equation is just the equivalent of this effective equation that I've just written here. And the solution of this Dyson equation can be formally obtained as inversion of these operators, where you have the self-energy and a single particle non-interacting Green's function that you can easily express in terms of the single particle energies that are the non-interacting energies. So this is a quantity that we are readily able to obtain, to calculate, and the self-energy is introducing all the effects related to exchange and correlation. And from the imaginary part of the Green's function, we can calculate the spectral function. So formally, this is the expression that is explicitly written in terms of the real and imaginary part of the self-energy. The self-energy is a complex object, contrary to the Conchamp potential that is real. The self-energy has a real and imaginary part. So both contribute to the imaginary part of the Green's function and to the spectral function. And the description of the spectral function in terms of this more complicated object is much richer than in the case of the non-interacting picture. So in addition to these single particle levels, you have other features that are described by the contribution coming from exchange and correlation that is encoded in the self-energy. And in particular, the real part of the self-energy is renormalizing the energy of the peaks. So it's moving the position of the peaks, and the imaginary part of the self-energy is inducing a broadening of these peaks. So each of them is moved and broadened, and the imaginary part of the self-energy is also adding new feature in the spectral function. So all in all, instead of having a single peak that is very sharp, you have a peak that is more broad, which is still a prominent peak very often. And this prominent peak that has a different energy and it is a different broadening, it's called a quasi-particle peak. It's the dominant contribution in the spectral function. This is what still defines the band structure in an interacting picture. But in addition to this, you also have other features that are called side bands or satellites that are a pure effect of exchange and correlation. This has something to do with the fact that when you remove one electron from the system, you are creating a positive charge in the material. And this positive charge is perturbing the system, and it can create additional excitation in the material. And you see these additional excitations as satellites. For instance, this additional positive charge can induce the collective excitation of the charge that are called plasmons in the material. And you see these additional excitations as additional features in the spectral function. And these would be plasmon satellites. So these satellites are due to the coupling of the whole of the positive charge in the material and additional neutral excitation that has been created by the fact that this positive charge is a perturbation in the electronic system. Again, this is a pure effect of correlation and it cannot be captured in a single particle picture. So the description in terms of Green's function requires a more complicated object because it has to describe a richer physics, which is related to normalization, related to broadening of the peaks, and to the creation of these additional satellites. Now, all this is in principle exact for the one-body Green's function. And in the case of the one-body Green's function in this more complicated auxiliary system, we have the same problem as in the Constant system. We need to make approximations for this self-energy, this effective potential. The advantage of the Green's function framework is that we can define effective particles. For instance, we can define effective quasi-particles, and we can have an intuition of the physics that we want to describe. Instead, DFT is a many-body theory of a collective variables, which is a collective variable, which is the density. In DFT, we have Constant electrons, but no one has ever met a Constant electron. So it's not something that we can measure. We cannot use our intuition about the physics. This is something instead that we can exploit in terms of Green's functions. There are different ways to approximate this self-energy. One way of approximating the self-energy is very similar to LDA, and it's developed in the framework of dynamical mean field theory, where we express the self-energy as a functional of the local Green's function, where local means that we just take a particular part of the Green's function in a particular space, in particular in the orbital space, and we are interested just in this reduced part of the Green's function, and we express, we make an approximation of the self-energy as a functional of just this reduced Green's function. But this is not what we typically do in many-body perturbation theory and in what you will discuss in the rest of the school. Instead, what we do in many-body perturbation theory, we just follow the propagation of this additional particle that is what the Green's function describes. And you have already seen that you can follow these different stories that have to do with the effects that are related to the propagation of this additional particle, drawing Feynman diagrams. So whenever you have an arrow, this corresponds to the propagation of one additional electron in the system. And then you can think about what this is causing on the rest of the system. And this can be expressed in terms of interactions. So you have the Coulomb interaction that is represented by the dashed line. And you can think that this additional particle is scattering with the density inside the material. And this density in the language of Feynman diagrams is represented by a circle like this. So this corresponds to the R3 potential, the R3 term in the Hamiltonian. It's the scattering of the additional particle with the density. You can have exchange diagram like this one that corresponds to the Fock exchange in R3 Fock. And you have more interesting diagrams where you have more interaction lines. And in particular, we'll be interested in this kind of diagram where the additional particle in the system is polarizing the medium. And this polarization is represented here by this ring diagram, also called bubble diagram, where you have the propagation of one other particle and the propagation of a particle with the reverse sign, because the error in this way has a reverse sign, and this is corresponding to the propagation of one hole. So you see that you can understand this diagram as the fact that this additional particle in the system is creating an additional electron hole in pair in the system, and this is associated with the polarization of the material. That is related to the fact it's a consequence of the Coulomb interaction, and it's a consequence of the fact that the system, the medium, is seeing the presence of an additional particle in the material. And these polarization diagrams are those that are creating a screening, a reaction of the material for the presence of this additional particle. And all this is something that we have to take into account, and these effects are all encoded in the self-energy. Okay, so the self-energy is just a collection of all these possible stories that are that we have to keep track, and that are a consequence of the fact that we have an additional particle in the material. And the spirit of making approximations in the Green's function functional theory framework is just that we have to select the most important stories, the most important physical effects that we have to take into account. And in the physics of the GW approximation, in particular, we take into account in the self-energy, the exchange effects, plus these polarization effects, these screening effects. And the GW approximation is called GW because the self-energy turns out to be the product of the one-body Green's function and the screening Coulomb interaction W. And the screening Coulomb interaction W is screened by the inverse dielectric function. And instead of having this bare Coulomb interaction V, you have this screening Coulomb interaction W, and the difference is given by this inverse dielectric function that is describing screening. And this screening is related to this polarization, this creation of additional electron hole pairs in the material. So the GW approximation is describing the coupling of the additional electron or the additional hole with electron hole pairs in the material that are screening the propagation of this additional particle in the material. So Matteo, you can understand.
Yeah. Sorry to interrupt. We are reaching the question time, so if you have time for a few more
slides. Okay, thank you. So the GW approximation can be understood as the propagation of a boat on a surface, on the sea, on the lake, and this propagation of this boat is creating waves, and these waves are those that are describing this polarization. And this is in contrast to artery fog, and artery fog can be understood as ice skating. So you skate on ice and the ice is not reacting, so it's completely frozen. It's not able to polarize, to react for this perturbation. So in GW, you take into account these additional waves in the propagation. And GW is today the standard approximation to calculate band structure, and it's in very good agreement with experiments. So these lines were calculated in the GW approximation by Rolfing and Louis, and it's also correcting the artery fog overestimation of the band gap. Now, GW is not only able to calculate, to give us the band structures, but is also able to go beyond this quasi-particle description, and it's also able to give us satellites. And this is related to the fact that we can also calculate this frequency-dependent object that is the self-energy. And here it's an example, and then I will conclude with this. It's the photomission experiment of bulk aluminum in the middle panel. And this is compared the calculation of the spectral function on the left that is calculated in GW plus cumulant. Cumulant is just a vertex correction to the GW approximation. But let's say this is a calculation of the spectral function. And you see that the main feature is this one that corresponds to the band structure of aluminum. So you have just a parabolic band. And in addition to this, you have replicas that are here, that are satellites. And if you measure the distance between the band and the satellites, these are equal to the plasmon energy of aluminum. So we can understand them as plasmon satellites. And you see that this GW plus cumulant calculation for the spectral function is able to capture the physics, but it's not in a quantitative agreement with the experiment. If you want to be in quantitative agreement with the experiment, you have to take into account all the phenomena that are related to the photomission experiment itself. And if you do so, then you can get a good agreement, quantitative agreement with the experiment. This is what we have done in this right panel. And this photomission spectroscopy will be the subject of the next lecture by Paulina, so you will get more details about this in the following. I will skip the discussion about excitons, but I'm sure you will have the occasion to discuss about exciton in the rest of the week. And I will just go to the conclusion, and the conclusions are the fact that we use Green's functions because observables we are interested in spectroscopies, the different spectroscopies are linear functionals of the Green's function. So these are non-functional of the Green's function. If you calculate the Green's function, you can obtain directly the spectra. And perturbation theory gives us a very powerful way to devise approximations because it's related to an intuitive picture of propagation of additional particles in the system, in the electronic system, something we cannot do in Conshan. And in particular, I have discussed the use of the one-body Green's function for electron addition and removal energy. And you will see in the following that you can use the two-body Green's function for the calculation of electronic excitations associated to absorption and other spectroscopies that are measuring neutral excitations like electron energy loss spectroscopy and elastic X-ray scattering spectroscopy. And the frequency dependence of the self-energy and other kernels brings us information that is beyond the quasi-particle picture. And with this, I would like to thank you for your attention. If you want to know more information on our activities, in particular on what Lucia is doing, you can look at the website. Lucia has also prepared an online Coursera MOOC on density fractional theory. This is the address. And there is also a book written by Lucia on many body perturbation theory, on Green's functions and quantum Monte Carlo. And this is the book. And with this, I would like to thank you for your attention, and I wish you fun with Green's functions and the rest of the school.
So thank you very much, Matteo, and the session is open for questions, if you have any. Or maybe, Matteo, I can start with one. So, of course, in your group, you have, I would say, the most expert group on satellites. And you have shown this last example where there is this plasmon satellite in the photomission spectrum of bulk aluminum. And as far as I understand, you can have a plasmon satellite because of correlation effects, what you have described. But you can also have some kind of plasmon satellite because of all the effects which we do not account, the fact that we compute the spectral function, but then the electron is going out and exciting possibly other excitations. So can you comment on that? Is there a way to disentangle when a satellite is correlation driven and when it's not?
Yeah, okay. So first of all, we are not the most expert group on this, but we are one of the groups working on this aspect. And the reason is that satellites are a qualitative feature of correlation. So if there is no correlation, you don't have satellites. So this is interesting per se, because it's really a fingerprint of correlation. Yes, then to answer your question, yes. So in a calculation that is just a calculation of the spectral function, there is no photon energy dependence. So the spectral function doesn't depend on the photon energy. Instead, experimental spectra do depend on the photon energy. And there is always a contribution of the outgoing photoemitted electron. And this outgoing photoemitted electron can also scatter on the way out from the material, and it can also induce plasmon satellites as the hole that is left behind. And then there is also an interference effect between these two effects. So all these contribute to plasmon satellites, and not only. And this is photon energy dependent. So this is the step that we have to take into account when we go from panel A on the left to panel C on the right. And this is very important if you want to reach quantitative agreement with the experiment, indeed. And very often we discuss about strong correlation effects, so corrections to correlation, because we find deficiencies in our description of photoemission spectra. But often I have to say that most important effects come from the fact that we are not calculating directly what is measured. What is measured is the photoemission spectrum. And if we calculate the spectral function, this is not exactly the same thing. So there is a gap between the spectral function and the photoemission experiment. And indeed, we have put a lot of effort to go beyond this spectral function description for photoemission. It's very important to try to work together with the experimentalists to bridge this kind of gap.
Okay, so
I hope
Matteo.
This is now clear.
Maybe we can start with the questions online. Yeah, Andrea.
Singh, Mukesh Singh, maybe he can do the question himself. No?
Okay, so can you try to unmute yourself? The name is Mukesh Singh, if I spell it correctly. Okay, maybe we can read the question.
So the question is, sir, how do we know that? How do we know what term should one use for the calculating self-energy?
I guess that you are referring to this. It's so in principle, the self-energy is describing all the exchange correlation effects in the electronic system. So if you have it, you have the exact answer for the one-body Green's function, so you calculate it exactly. In practice, we have to make approximations, and the approximations are related to the physics that you need to describe. And the advantage of Green's function theory is that you can keep track of the physics because you have these effective particles that are interacting in the material. And you have to, as always in life, you have to make a choice. And the choice is related to the most important physics of your material. And in the case of the GW approximation, it's a specific case. We make the choice of saying, of identifying the most important physical aspect, that is screening. It is this polarization of the system for this propagation of this additional particle in the material. It's not the only choice. There are different choices that can be made. In particular, in the Green's function formalism, we can associate approximations with couplings. In the case of the GW approximation, we describe this screening physics in terms of couplings between quasi-particle and neutral excitation of the charge, so electron pairs associated to the charge. And for instance, we completely miss the coupling with spin excitations, which are the other kind of bonds. And so if your material, your system of interest has this specificity that this coupling is important, you should choose other diagrams. So the choice is related to the physics.
Thank you, Matteo. And I read another question from a student online. So it's actually a double question. So the first one is, what does it mean to speak about non-locality in time? And then the second question is, why the name self-energy? So why do we call it self-energy?
Non-locality in time, it's due to the fact, we can understand it from the fact that the Green's function is a propagation of a particle from a time t to a time t prime. Okay, so this is giving us already one reason why we have no locality in time. The second reason, indeed, is more subtle, in the sense that the many-body Hamiltonian is static. In our case, it's not time-dependent, so we have a static problem. And when we introduce the self-energy, we make a choice, which is we want to avoid to take into account explicitly all the many-body possible excitations in the system that are 2-particle, 3-particle, 4-particle excitations, and we fold all these many-body excitations in a frequency-dependent effective potential that is the self-energy. And this is like an embedding strategy, okay? And indeed, self-energy, it's called in this way because it's a way to describe the effect of the other excitation on the particle itself. So this is one of the reasons why it was called self-energy.
Okay, so I think we have time for one last question, if there is any from the audience here, otherwise we can pick up. Oh, sure.
Hello, sir. Am I audible?
Hello?
Hello. So my second question was that, let's say if we put the self-energy in quantum equation, will it improve the results?
Will improve, sorry?
Will improve the result, maybe energy and band structure.
Okay. Again, it depends on what you are interested in. If you are interested in the density, the Kohn-Sham system is enough because the Kohn-Sham system is meant to give us the density. If you are interested in the band structure, you cannot use the Kohn-Sham system because the Kohn-Sham system is an auxiliary system. So it's a system of effective particles that are auxiliary particles that are just meant to give us the density. And you have to introduce a different framework, and in particular, the Green's function framework, where you have this effective, more complicated object that is the self-energy, with this effective, more complicated auxiliary system, is meant to give us, for instance, the band structure. Then the quality of the results of this more complicated framework depends on the quality of the approximation for this exchange correlation self-energy. So if you make a good approximation for the self-energy, you get good results. If you make a bad approximation, you still get bad results.
Okay, sir. Okay, thank you. So one more thing, maybe follow-up question. Is there any other thing apart from the density of state, which can be calculated from quantum equation exactly?
Not the density of states, the density.
Yes, sorry, density.
Okay.
Apart from that.
In principle, you could calculate from the density and DFT. You know that in principle, you could calculate all the observables as functionals of the density. Okay, this is what DFT tells us.
Yes, but we don't know the operator you told.
The problem is that for most of the cases we are interested in, we don't know this functional. Okay, so in some cases we have good approximations to the functional. In particular, for the total energy, we know that we can have good approximation to this functional, which is also implicitly unknown, but we have good approximations. The LDA, the PBE, these are the widely used functionals. So for the total energy, we can obtain good estimates. For quantities that are related to spectroscopy, this is much more difficult. So in particular for band structures, we don't have these functionals. So we don't have it.
Okay, so maybe
how do we know that the...
We move to the last
Okay,
question from a person here in presence, and then we have to move to the next talk. So you can put the question on the chat, and we will try to address it. Okay, sorry.
Okay, thank you, sir.
Okay, so how do you build this Green's function? So if from the equation you're showing, I mean, we basically compute this from the Comsham eigenstates. But like, so when computing this self energy, we do some Dyson expansion. So we have like, for example, higher order Green's function terms when we do this expansion. So how do you compute these things? Because this is like an independent particle level, at an independent particle level, but somehow you have to include some interactions between these things. For example, if you're computing the dielectric tensor, for example, in the when you're doing this thing, we have to compute the dielectric tensor. So the imaginary part of the dielectric tensor is somehow related to the, we have to consider the interaction between the electron and the hole. So how important are these, like when doing these things? Because when you're doing the GW, I guess we don't consider these effects into, so like how important are these effects in the band gap, like correcting the band gap and the bands?
Okay, many questions, but I try to be synthetic. So you calculate in this Dyson equation representation, you can calculate the Green's function just by any approximation of the self-energy, okay? Because this G0 is something that you can obtain directly from the single particle energies. All the exchange correlation effects beyond the single particle description are encoded in the self-energy. So anything that is related to interaction is in the self-energy. Any approximation to the self-energy can be used to calculate the Green's function. How you do this in practice, you will see when you do, for instance, GW calculation in practice with Yambo. How this is important, the effect of the self-energy is represented here on the spectral function. So you go from this single particle picture where you have sharp peaks to this richer description where you have peaks that are broad and where you have additional features. How this is important for the band gap, I would say not only for the band gap, but for the band structure in general, and for effects beyond the band structure that are satellites. An example is here for germanium. So instead of having a metallic material as in LDA or a very large gap as in Artifoc, you are in much better agreement with the experiment. And the difference between GW and Artifoc is in the screening. So you have to calculate the electric function that is the screening. And you will do this in practice. So don't forget to come also in the next days to the school.
Okay, so thank you again, Matteo.